Okay, so I solved for C, and a really common mistake is to circle C equals cosine 3 minus 1, right? But that's just a piece of the solution, right? The actual answer is the function y equals negative cosine x plus 2x plus the C that you just found plus cosine of 3 minus 1. And that will be the answer to the initial value problem. All right, so we just did a pretty simple differential equation, right? We just had to come up with a function whose derivative was something that was given. Differential equations can get pretty complicated. For example, here's one, 4x squared times y double prime plus 12xy prime plus 3y equals 0. It's harder to just think like, what's a function y so that when I take its second derivative and multiply by 4x squared and add 12 times x times its derivative and then add 3 times the function, I get 0. Like that's like, I can't do that in my head, right? Someday we'll be able to do something like this, solve that. But for now, I'm giving you the solution, or giving you a solution, x to the negative 3 halves, a potential solution. And we just want to check it, right? Just think about like when you first learned how to solve basic equations. Like if I have the equation 3x plus 5 equals 14, right? Okay, so pretend you don't know how to solve it, right? This is before you learned how to move things around in an equation. If you don't know how to solve it, you could check x equals 3 is a solution, right? Somebody tells you that or asks you, is that a solution? How do you check? Plug it in. So you go, okay, 3 times 3 plus 5, does that equal 14? Yes. So you get 14 equals 14. Both sides are the same. It's a solution. If I had asked, is x equals 2 a solution, right? You would go 3 times 2 plus 5, does that equal 14? And you'd have 6 plus 5 is 11, doesn't equal 14, so no. This one's a yes, this one's a no. You just plug in. So that's what we're going to do with the differential equation too. We're going to just plug in to see if something, a potential solution really is a solution. So y equals x to the negative 3 halves. Now my equation has y and y prime and y double prime in it. So if I know y, I have to figure out y prime and y double prime in order to be able to plug in. So what is y prime if y is x to the negative 3 halves? Good. Negative 3 halves x to the negative 5 halves, just power rule. And then y double prime, power rule again, and I'm going to get 15 fourths x to the negative 7 halves. All right, so now I got to check. Over here, I'm going to do my checking. So I have to check, does 4x squared y double prime plus 12xy prime plus 3y, does that actually equal 0 when I use the y that they gave me and the y prime and the y double prime that I just calculated? All right, so I'm copying 4x squared, and then I'm plugging in y double prime, 15 fourths x to the negative 7 halves, plus 12 times x, replace y prime with what I found, negative 3 halves, x to the negative 5 halves, plus 3 times y was given, x to the negative 3 halves. And I want to know, when I simplify that all out, do I get 0? So let's see, these 4's cancel. X squared times x to the negative 7 halves, that would be, add the exponents, so 4 halves and negative 7 halves is negative 3 halves. 15x to the negative 3 halves plus. All right, and then I simplify this. That's negative 18 x to the -3/2 plus 3x to the -3/2. Does that add up to 0? Yes, those are all like terms, x to the -3/2. 15 minus 18 plus 3 is 0. So because the left side equals the right side, this is a solution. So yes, it's a solution. Does that make sense? So today, that's the only analytical thing we're going to be able to do. In fact, for a couple of days, that's the only analytical thing we're going to be able to do. Rather than being able to actually set out and solve the equation, all we're going to be able to do for a few days is check if something that I give you is a solution. All right, but let's talk about why we want to be able to solve differential equations. So differential equations model many, many physical situations. And we call the process of using a differential equation to describe a physical situation modeling. So we're going to look at modeling several times throughout this class. It's going to be a big theme. And the steps are to state your underlying assumptions. So you have to have some assumptions about how the world works in order to be able to translate those into an equation. Then you're going to identify relevant variables and parameters, and then use the assumptions to formulate some equations. All right, so let's think about the US population. So the first, most basic model that's used for population growth is called the Malthusian model. And the assumption of the Malthusian model is that the growth rate of a population is proportional to the size of the population. That means that as populations get bigger, they grow faster, right? As there are more and more members of the population, they reproduce faster and faster and faster. So that's our assumption. And so our variables, thinking about this assumption, the growth rate is a speed or a rate of change. The growth rate of the population is proportional to the size of the population. So the main variable here is the population size. So let's have that be P. Okay. So size of the population, P. Growth rate of the population, how would we symbolize the growth rate of the population? dp dt. Growth rate of the size of the population. Okay, so my Malthusian model, the only thing left to translate is this word is proportional to, right? So if A is proportional to B, what does that mean? Sorry. Yeah, their ratio is constant. Translating it to an equation, you could say, well, their ratio is some constant, right? Or you could say that A is some multiple of B. Right. So to write this as an equation, it says the growth rate is, so the growth rate, dp dt, is equals proportional to the size of the population. So proportional to or some multiple of the size of the population, P. So that's sort of our most basic population growth model. It accurately translates the assumptions. Those assumptions may not be correct. And we'll look at some more and more complicated models that challenge that assumption. But this is called, this Malthusian model, it's called a first order differential equation because it contains only first derivatives. And it's called an ordinary differential equation because it doesn't contain any partial derivatives. which I'm sure you studied in Calc 3, partial derivatives, right? We're not going to be dealing with any partial derivatives in this class. This is an ordinary differential equations course. So no partials. All right, so I want to confirm that P of t equals a 0 is a solution to the Malthusian model. Okay. So if my population size is 0, then I want to say that this works. Right, so I'm just going to do exactly what I did over here, checking a solution. It's just that my function y of x is a really simple function, y of x equals 0. So let's see, I want to show P of t equals 0 solution, right? Is that a solution? So my equation has P of t in it and dp dt. So I've got P of t equals 0, then what is dp dt? Also 0, derivative 0, 0. Now I want to show, is my equation true using this P of t and this dp dt? Okay, so my derivative is 0. That's what I just calculated. Copy the k. P is 0. That was given, right? 0 equal k times 0. True, right? No matter what k is. So a population that doesn't exist never grows and always stays 0. So P of t equals 0 is a solution. And this is called an equilibrium solution, this P of t equals 0, because it never changes. P of t equals 5 would also be an equilibrium solution, right? Because it's just a constant, never changing amount of people or rabbits or whatever. Okay, so I'm going to have you work on some activities in your groups, and then we'll spend like maybe half an hour at like 9 o'clock-ish. We'll come back together and start lesson 2.